In this lesson, we will be defining exponential growth, asymptote, exponential growth factor, and growth factor. We will also be graphing exponential growth functions and using these exponential growth functions to model real-life situations. First, we're going to take a look at the exponential function, which is y equals a times b to the x. Now the parent function is y equals b to the x, where the a value is 1. In the exponential function, our a is the vertical shrink or vertical stretch, and b is the base. If a is greater than 0 and b is greater than 1, we call this an exponential growth function. Taking a look at the graph we have below, our function is y equals 2 to the x. This is a great example of the parent function because our a value is 1. We'll take a look at it by first plugging in some x values, -2, -1, 0, 1, and 2. Now this function is a little bit different than something we've graphed before because now our x is in the exponent. So if we plug our x values in, we get 2 to the -2, which we know is 1/4. And so on, 2 to the -1, which is 1/2, 2 to the 0 power, which we know is 1, 2 to the first power is 2, and 2 squared, which is 4. From there, we take our points over and plot them. -2, 1/4 we have right here, -1, 1/2, and so on till 2 and 4. Now, one thing that I want to point out is when we're graphing these exponential functions, we have to pay close attention to what our a value is. In this function, our a value is 1, which we know is a positive value. When we have a positive a value, we know that our graph is going to start from the left, move to the right, and also go up. Sometimes we're not as lucky to have so many points plotted when we make our graph, so it's good to know the direction in which our graph is going so that we can follow that pattern when we follow our points. Another thing that I want you to take a look at is this piece of the graph. It's getting very, very, very close to this x-axis, but it never actually touches. We call this an asymptote, which, as a reminder, is a line that a graph approaches as you move away from the origin, but never actually touches. So in this case, our asymptote would be y equals 0. Let's take a look at our first example. Y equals 2/3 times 2 to the x. Now, if you'll remember from our first slide, y equals 2 to the x was our parent function. So what we're doing now is we're changing our a value to 2/3. So when we graph these functions, the first thing we want to do is pick some x values. So we'll do -2, -1, 0, 1, and 2. Right after we pick our x values, the first thing we're going to do is plug them into our parent function. We're going to ignore the a first. So let's look at 2 to the x, which we just did on the previous slide. But as a reminder, we have 2, which is our b, our base, and plugging in our x, we get 2 to the -2, which is 1/4. Moving down, we have 1/2, 1, 2, and 4. The next thing we do is we now consider the a value. So we're going to take 2/3, which is our a value, times our f of x, which was our parent function. So if we take 2/3 times 1/4, we get 1/6. Moving down the line, we get 1/3, 2/3, thirds, 4/3, and 8/3. Okay, now what I like to do when I'm graphing this is to cross off this middle column so I don't get confused when I'm graphing the points. So we're going to look at the first point, -2, 1/6. which is right about here, and -1, 1/3, 0, 2/3, 1, 4/3, and 2, 8/3. Once again, we notice that our A value is positive, so we know that our graph is going to move from the left to the right and in an upward motion. So let's graph that. And just like the first slide, we have our asymptote here at the x-axis. Our asymptote is at y equals 0 because we never actually touch or go over this x-axis, y equals 0. One other thing, we want to compare this function to the parent function. If we look at the graph, what did we do? In the definition, we said that our A value was our vertical shrink or our vertical stretch. Notice that this 2/3 stretched out our original parent function graph. So we would say that 2/3 is A is a vertical stretch to our graph. Moving on to our next example, we have y equals -2 times 2 to the x. We'll start just like we did before by picking some x values to plug into our equation. Start with the parent function, which once again is 2 to the x. 2 to the -2 we know is 1/4. Moving down we have 1/2, 1, 2, and 4. Now once again we want to take our A value, which this time is our -2, times our parent function. To get -2 times 1/4, which is -1/2. Moving down, we have -1, -2, -4, and -8. And just as I did in the first example, let's just go ahead and cross off this middle column so that we don't get confused when we're graphing. Our first point is at -2, -1/2. Our next point is at -1, -1, 0, -2, 1, -4, and 2, -8, which is somewhere down here. So let's look at our A value one more time. We notice that this time we have a negative A value. So we're still going to move from left to right, but because our A value is negative, we're going to go down. Just as Mrs. Dallin always says, if you are negative, you are a downer. So just remember, when our A value is negative, our graph is going down. Okay, one more thing I want to point out. Our asymptote is still at the x-axis here, but this time we want our y values to be below the x-axis. So our asymptote is still at y equals 0, but because our A value is negative, our graph is now below the asymptote. The next type of equation that we're going to be looking at is called the general exponential function. Now this, if you'll notice, is very, very similar to our first equation with the parent function, except for now we're adding transformations. So y equals a times b to the x minus h plus k. So our h value is our horizontal transformation of our graph, and the k value is our vertical transformation. So you'll have your parent function in there still, which as a reminder we have y equals a times b to the x. But now we're going to look at our transformations. One more thing that I want to point out to you guys is that our h is negative by default. So when we're picking out our h value, we notice that in this equation, h is actually 2, okay? And then our k value is 1. From here, what we're going to do is notice that our hk coordinate is 2, 1. This is going to be our new origin. Okay, so let's first start by graphing the point 2, 1. Since this is our new origin, we're also going to need new axes. So next, what I'd like you to do in these problems is draw your new axes coordinates around this new origin point. Okay, so we have our new origin, we have our new axes. Now what we can do is just begin, as we did before, by graphing the parent function. So if we take out the transformations, we're left with y equals 2, what just happened? 2 times 3 to the x. Okay, so again, we'll start by picking some x values, -2, -1, 0, 1, and 2. Plug that into the parent function, which is 3 to the x. So 3 to the -2, we have 1/9. Then we get 1/3, 1, 3, and 9. Okay, and then we want to consider our a value. So now we have 2 times our parent function, which is 2/9 and 2/3, 2, 6, and 18. And just like before, let's cross off this middle column so we don't graph any of those points. Now if we're going to graph this, we start at -2 from our new origin. This is our new 0, 0. So -2, 2/9, -1, 2/3, 0, 2, 1, 6, and 2, 18, which is somewhere probably way up here. All right, so now that we have our new points, our new origin, and our new axes, we are going to graph that line. Okay, so there is the graph of our y equals 2 times 3 to the x minus 2 plus 1. Notice that our new asymptote is now at y equals 1, because that is where our new axis lies. The domain in this function is all real numbers, and the range is going to be y is greater than 1, because we want it to be above this asymptote line. The next topic we're going to cover involves using exponential growth models. When a real-life quantity increases by a fixed percent each year, the amount of y of the quantity after t years can be modeled by the equation y equals a times 1 plus r to the t power, where a in this equation is the initial amount, r is the percent increase expressed as a decimal, and the quantity 1 plus r is our growth factor. So let's take a look at an example of a growth factor model. In 1980, about 2,180,000 U.S. workers worked at home. During the next 10 years, the number of workers working at home increased 5% per year. First, we're going to write a model giving the number W in millions of workers working at home T years after 1980. So, first we're going to begin by writing out our equation. So it says, write a model giving the number W, so equals our equation A times 1 plus R to the power of T. Then we're going to figure out our variables. So our initial amount A is going to be the number of workers in millions, and our initial amount is 2.18 million. And then our percent of increase was 5%, which is 0.05 in decimal form. And then we substitute in our numbers, so now we have W equals 2.18 times 1 plus 0.05 to the t power. Now remember, this one equals your r. So if we simplify, we get W equals 2.18 times 1.05 to the t power. The next question is to graph the model. Notice that this equation looks very similar to the parent function that we just graphed in the first few slides of this video. Our b value is the 1.05, which is the base, and our a, 2.18. So we're going to start just like we did before, and we're going to pick out some x values, which in this case is t. Do you see that? In our equation we have t, so our t is going to be our x-axis, just like it was in the parent function equation. So let's pick some t values. We're not going to pick negative because our time can't be negative in this example. So if we look here, during the next 10 years, I look at this number and I say, okay, we're going to start with no years, we're going to go to 10 years. So I'm going to go by 2's on my x-axis so I can cover all these 10 years that they're talking about. So we have 2, 4, 6, 8, and 10, and of course 0 here. And then our f of t is going to be our w. So if you take your calculators out, first we can look at this one. Anything to the 0 power is just 1. So 2.18 times 1 is 2.18. I've already calculated these other ones out ahead of time. So we have 2.4 here, 2.7, 6 is 2.9, 8 is 3.2, and 10 is 3.5. Next, we'll plot these points. So 0, we'll go regular scale on this side because we are only going in up to about, as we can see, 3.5 million here. So we'll just go 3 and 4. Okay, so we have 0, 2.18. Let me get a different color so you can see that a little better. Okay, 2, we have 2.4. Okay, 4, we have 2.6. 6 is 2.9. 8 is 3.2. And 10 is about 3.5. Not as steep of a graph as we've had, but that's all right. We're still going up. We're still curving. Now the next question says, use the graph to estimate the year when there were about 3.22 million workers who worked at the home. There are two ways to do this. What it wants us to do is to look where our value is at about 3.2 million workers. And we know that workers is our w-axis over here. So if we look around about 3.2 and we head on over to the graph, we can see that we're right down here where we plotted 8. Now since we started this graph at the year 1980 and we went 8 years, we know that there were about 3.22 million workers who worked at home in the year 1988. Okay, and the other way to do this, we got kind of lucky. We picked 8 to be one of our values, so we could have just looked over here and said, Well, we got 3.2 million at about 8 years. So 1980 plus 8 years, 1988. The last idea that we're going to be reviewing in this video is compound interest. This is the interest paid on the initial investment called the principal and on previously earned interest. Interest earned is expressed as an annual percent. So if the initial principal P is designated in an account that pays interest at an annual rate R, expressed as a decimal, compounded n times per year, the annual amount A in the account after T years can be modeled by this equation. A equals P times the quantity 1 plus R over N to the NT power. Now this is a lot of information to process, I understand that. Writing these things down is going to be vital, because in these compound interest problems, we are mainly focused on finding our variables and plugging them into the equation. So make sure you take some time to write those down. Let's look at an example. Let's say we deposit $1,500 into an account that pays 6% annual interest. We want to look at how we can find the balance after 1 year if the interest is compounded annually, semi-annually, and quarterly. So first we'll take a look at the annual version. Let's find our variables. P, which we know is the initial principal, is $1,500. That's what we start with. Okay. Next we want to find R, which we know is the rate annually expressed as a decimal. So we have 6%. Our decimal is 0.06. N, which is our times per year. If we are moving annually, that means we're doing it once a year. So our N equals 1, and T is how many years? And it says after 1 year. So our T is also 1. Now all we have to do is plug these numbers into our equation. So our A equals 1,500 times 1 plus 0.06 over 1 to the 1 times 1. Simplify this, work it out on your calculators. We find out that our A is equal to $1,590. So it says find the balance after 1 year if the interest is compounded annually. Our balance is $1,590 after the balance was compounded annually. Next we're going to look at quarterly. This problem has not changed, so most of our variables are going to stay the same. Now it wants to look at if our balance is compounded quarterly. So our N value is going to change because quarterly means 4 times a year. So if we plug those values back in once again, we get A is equal to 1,500 times 1 plus 0.06 over 4 to the 4 times 1 power. And if we put that into our calculators, we see that the value is now $1,591.35. So if we do it quarterly, we get about $1.35 more. Now let's see what happens when we compound daily. We know that there are 365 days in a year. So if we compound this daily, plugging those numbers in, 1,500 times 1 plus 0.06 over 365 to the power 365 times 1. If we are compounded daily, we get $1,592.05. So we find that the balance after 1 year, if the interest is compounded daily, is the most beneficial to us because it's up to $2.05 greater than if we just compound annually. Now there was a lot of information in this section, so I want to make sure you take a good chunk of time to review. First, we went over the exponential function, which was y equals a times b to the x, where the parent function was y equals b to the x and the a value was 1. Remember, in the exponential function, our a value is the vertical shrink or stretch, and the b value is the base. In the general exponential function, our y equals a times b to the x minus h power plus k. This is just like our parent function, except for we're adding in h, the horizontal transformation, and k, the vertical transformation. Next, we went over how to use the exponential growth model, which is y equals a times 1 plus r to the t, where a was the initial amount, r was the percent increase, and the quantity 1 plus r was our growth factor. And last, we discovered the compound interest formula. A equals P times 1 plus R over N all to the NT power. P, the initial principal, R was the annual rate, N was the number of times per year, and T is how many years.